So good morning and Assalamualaikum. Sorry for the delay. There was some technical problem with my laptop. So let me go to the lecture notes. Can you guys see this? Okay, great. So we come to the point of well, okay, and let me just recall what we did in last lecture. So in last lecture, we introduced the idea of perturbation theory. So the only assumption, so previously we had perturbation theory being introduced formally, and then some example. But assumption over there essentially is okay that your energy eigenvalues that we have are essentially non-degenerate. There are there is a possible resolution to this, particularly if you use a different observer to label your label the eigenstate. Label the state of the system, provided there is a compatible observable A, C, okay, and this is compatible to the Hamiltonian. So you can actually essentially label your states using both the eigenvalues of your Hamiltonian and also the eigenvalues of your observable A. So in other words, the non-degeneracy might be in the Hamiltonian, but your A itself might have, your degeneracy might be happening for the Hamiltonian, but your compatible observable A might have non-degenerate eigenvalues. So in other words, in that particular case, that would sort of resolve the problem with respect to labeling the states of your physical system. Okay, but that doesn't quite solve the things that we need. For example, when we talk about energy shifts, so the energy shifts would actually involve the eigenvalues of the energy, for which if there are degeneracies, then one need to deal with that specifically. So what is the problem? If you look at the previous notes on perturbation theory, we have terms like this appearing in your in your corrections to the energy shift and also the eigenstates. Okay, so when you have the terms like this, if you look at the denominator, there's a possibility that these two states involving the n level energy and the k level energy might be coming from states which are degenerate. So in other words, this becomes zero at the denominator, and of course, you do not want that, because that will give you an infinite quantity there. So we need to handle whatever it is. We need to handle this idea of energy degeneracy at least. Okay. So the other thing is the fact that suppose you have a few states which has the same energy. That's a possibility of use. See, essentially, if you remember from the first course, suppose you have A and B here have say the energy E naught, for example. Okay. Then so both have E naught eigenvalue. Then you also know that you can always take a linear combination of this. Okay. And this will have E naught as well as your eigenvalue. So that is pretty obvious if you just you look at the first course, how we actually show that this is actually having the same eigenvalue by just simply adding your Hamiltonian onto the superposition thing. So in other words, a possibility is to consider different basis states to this. Suppose these are going to be basis states, okay, your A and B. One can choose a different basis state besides A and B. One can have linear combinations. And why is that useful is to consider the case where, in this example, where you have the connection between the N and K states, you would prefer that your potential matrix element here to be sort of zero. And that will actually solve this problem with degeneracy. So here is what we're going to do. So we have this freedom of choosing the basis within the subspace of states which has degenerate eigenvalues. So we normally call this subspace to be D. Okay. And then let's assume the multiplicity of this degeneracy is essentially G4, meaning there are G different states that has the same energy, say ED naught, okay, and then this G different states are given by this states M naught, for example. Okay, so our desire is essentially to use linear combinations of this M naught to give you a different sort of basis states in the degenerate subspace, okay, the degenerate subspace D, such a way that the perturbation sort of perturbation term that we're going to have will have zero numerator. So in other words, you can actually solve the problem with the degenerate terms. Okay, so that's what we're going to do. And then the other thing that we must have in when you do that, you would also have to be careful with respect to taking the limits of your perturbing parameter. Lambda goes to 0, that it should get to the state that you want. In this particular case, it will be some unperturbed state. Okay, so the perturbation potential would be in this case would be just to remove the degeneracy. So in this particular case, we sort of modified slightly the problem of the perturbation theory just to focus on the degenerate subspace, and then sort of use a kind of potential that sort of remove that degeneracy. So okay, so what we want to do is now to go to this a new set of unperturbed states L naught, okay, for which L naught can be actually written as superposition of your previous degenerate states. Okay, so this is a sum over the degenerate subspace, and then this is the coefficient. Okay, so it's just the normal state expansion that we had in the first course. So we introduce in this particular case, we introduce two projection operators. one projection operator on the subspace spanned by the degenerate states. Okay, so this essentially give you the basis of your degenerate subspace. The other projection operator is actually a projection onto the remaining states. Okay, so when we write down the Schrodinger equation, like the perturbation theory before, we'll have something like this. Okay, so this is coming from your earlier perturbation theory. So this is your perturbed state. Okay. So this equation is coming from your Schrodinger equation. Okay, and then you introduce the fact. Okay, the other thing that I should say is that P naught plus P1 is actually the identity, because P1 is just no, the orthogonal sort of projection there. So what we can do is to insert an identity operator there, and then you have this decomposition using the projections. So you have P naught here, and then you have another term which is projecting onto the other states. Okay. So the other thing that we need essentially is, because P1 is coming from a orthogonal decomposition here. Okay, you also have P naught times P1 equals to 0. Okay, so what one can do now is essentially to multiply this whole equation by either P naught or P1. Okay, so when you do that, you get two different equations, because this equation will be sort of broken down into two subspaces, one from the degenerate subspace, and then the other one will be the one orthogonal to it. Okay, so in this particular case we have 2 over here, so this is coming from P naught. So you can see that I multiply P naught over here, so I will get well, this is just eigenvalues, so your P naught comes here. When you okay, the other thing that you need for projection operators, P naught square equals to P naught. Okay, so when you say do for the case of E minus E D naught, P naught here, then you have the other one is P naught L here, for example, coming from this term multiplies that. So this is just eigenvalues, so this is equal to E minus ED naught P naught squared L, and then you use P naught squared equals P naught. Okay, and the other thing over here is V. V doesn't necessarily commute with P naught, so we have to maintain that. So you have that. Okay. So you have this from this term, and then we have another one from here. The one, so you should be multiplying P naught on this term. So the one with respect to this, P naught will commute with H naught, because it's just a projection operator in that case. But when it comes to here, it will not commute, because you have your perturbing potential. The case over here, when it commutes, will meet P naught will meet P1, and we can actually use that. Okay, I've forgotten. I should actually, you cannot see the cursor, right? Okay, so I have to remember that. So so in other words, over here what we have you only have left the lambda p naught v p1, so which is this term. So this is coming from p naught. P naught projections. So the next one will do the p1 projection. Again, it's just the same thing. So you multiply p1 here. So the one with the eigenvalues will just commutes with p1, and then p1 will multiply the operator v here, and then we get that term here to here, and then we have your p1 acting on here, and again the same argument. P1 will be commuting with this E minus H naught, but it will not commute with V there. So in other words, we are left with this thing. Okay, so you get two different equations coming from the projections into two different subspaces. Okay, so one has to remember the first equation is actually on the degenerate subspace, or the P naught subspace for short, and equation 2 is on the P1 subspace. Let's look at equation 2 first, because this can actually be solved essentially because this term over here is not going to be singular. Okay. See, yeah. What happens over here? We're trying to sort of rearrange these equations too, so that you can get a term which involves the P1L here. Okay, so in other words, I will have to bring this operator on the denominator. Okay, and you get to this point, and the projection P1 you can over here is coming from, let's see, oh yeah, I mean you can multiply another projection operator because of the same property, P1 squared equals to P. Okay, so in other words, this will give you P1 because of P1 squared equals to P1, but here you multiply P1 here onto this equation, which is coming from this particular term. Okay. And then you start again expanding in terms of, sorry, what's happening? And then you expand your eigenstates, sorry, your perturbed state with respect to the perturbing parameter in this way. Okay, so you have the zeroth term, and then the first order term, and so on and so forth, and then you plug this thing into your equation, and one should be able to write down the first order term P1L1, for example, and then let's see, and then you use P1 missing something here, lambda is coming from here and also here. Yeah, so in other words, we will only take, in this particular case, to get a linear term in lambda. Okay, So I would have to consider this multiplied with this lambda. So that will give you the linear term. So and that will reduce this to the following. I'm just going to check the denominator here. So this becomes I had it before. Let me just figure this thing out first. Okay, I'm just worried about this term. Okay, I'm a bit confused at the moment. The idea is essentially to equate the linear terms in here together with the linear terms in the left hand side and the linear terms in the right hand side. The one that bothers me at the moment is this particular term, but I guess in this case you just consider the case I have a projection operator here. Okay, let me just write that. So this projection operator is coming from the not from the degenerate subspace. So this is actually K naught. Thought I had this done. So this gives you that. Then I have also this. And this will only involve L naught. Let me just figure this thing out first. So L naught so this becomes so I would need another P1 here. Okay, getting confused here. But okay, somehow or other I would be able to reduce this to this. Okay, maybe I will have to do this again next time because I've done this before, but I just forgotten how I did it. Okay, anyway, so this is essentially your first order term. Okay, we'll come back to this at some other point. First order term in equation 3. Okay. And that gives you an equation which is in the non-degenerate part of the space. Okay, this equation is lives on the non-degenerate subspace. Okay, so we go back to the other equation. Remember we had two, so we had this one equation which we have not done so far. Okay, so over there you can see that this P1L is again coming here. So what one can do is to use this, but then you start to think, okay, that remember that this is actually for the non-degenerate subspace, or I should maybe I just call it non-degenerate P1 subspace. So I will just shorten it to P1 subspace. So here is an equation for P1 subspace. You inserted here, sorry, it's inserted over here. But remember, this is actually from the P0 projection, so it should be in the degenerate subspace. So what's going to happen over here? So what happens over here is the following. P1 acting on L, one can think of it, okay, I have your P1 subspace over there, but V would sort of mix up back your P1 subspace into a involving terms with a P0 terms. Okay. So in other words, we here sort of mix up back your terms from the non-degenerate subspace, okay, your P1 subspace, to include terms which involves your P0 subspace. Okay. And then over here, what is being done over here, this ensures that you only pick up those terms which are involving P0 subspace. Okay. So in that case, that sort of settles that, okay, this is still an equation. When you substitute this, which is actually in the P1 subspace, this is still an equation. Okay, this is P1 subspace. This is still an equation in the P0 subspace. Okay, so by inserting equation 3 into equation 1. Okay, so I hope that sort of justify the things that we do, okay, because it's a bit tricky over here that you have already decomposed into two different spaces. So when you do that, then we have a new equation for your P0 subspace given by this equation 4. Okay, so this is actually in P0 subspace. So now we can start to do the some form of perturbation theory. So over here you can actually look up for terms linear in lambda, okay, for your bracket terms, okay, this bracket terms over here, and then your state over here, you only take the zeroth order term. So that essentially because you do not want anything involving lambda coming from your state here. Okay. So that will give you this equation which sort of replaced. So this is sort of replaced the Schrodinger equation in the P0 subspace. Okay. So you have a slightly different thing to consider now. Okay. So you can think of this is like a separate equation for you to solve in order to get rid the problem with the degeneracy. Okay. So what one needs, okay, let's rephrase this like a perturbation potential here. Okay. So you want somehow rather to solve this equation, okay, in such a way that you get to the other basis. Okay, so you get to the other basis by solving your circular equation. Okay, so in other words, we what we need is so you get another set of lambdas, or set of eigenvalues, which correspond now to the shift, the energy shift. Okay, so solving this to get the energy shift eigenvalue, and then you start working out, okay, what for each energy shift eigenvalue, you start out working on what is the eigenvectors. Okay, and the first order shift is actually given by a similar formula that you have seen in the perturbation theory before, in the case of non-degenerate case, but over here is simply for the case of the degenerate subspace. Okay, and what we want is essentially to make sure that we use a different basis. Okay, remember the first basis that we used was m naught. Okay, and this correspond to this part. Okay, but now we are replacing with this L naught. Okay, so by doing so, we want it to have the matrix element for your potential will have vanishing of diagonal matrix elements. Okay, so it's a bit long-winded route to take when you do have all this degeneracy. So now we return to 4. Let me just recall what equation 4 is. That one. So we return to equation 4, which is in the P0 subspace. And then one keep terms up to lambda squared from there. So you keep that term in. Just now what we did was to restrict to the linear terms, and then now we keep the lambda squared term. And essentially, again, there's a slight modification. I think this is also correspond to some problem I had earlier with respect to this thing. So what we do in that particular case, we have to use the fact that we have this well, you remember your delta is just your energy shift. Okay, so we are going to use that equation into equation 4 earlier. Okay, and then that would actually remove the part of your lambda v, because we are going to insert this. Okay, so again, some of this is just a messy in terms of the algebra. So in the end, what we need to find is this first order eigenenergies corresponding to this thing. And what is this Vi here? Vi is the eigenvalues of your perturbing potential there inside the degenerate subspace. Okay, but now using the fact that we are using a different basis. Okay, so using the different basis, we do not want the degeneracy to occur. So your energy difference from two different states will not be zero anymore. So so essentially using that different basis states, you sort of leave the degeneracy that you need. Okay. All right. Sorry, this is when I first look at this kind of problem, is also a bit confusing in the beginning. So now one can actually write down the correction to the states in the degenerate subspace, okay, which is going to be corrected by this first order term involving this. Okay. So now we can put in your projection operators. Okay, so you have your P1. Remember, P1 is some K is not in the degenerate subspace. K not. Sorry, maybe I should not use the K not there, because here we are limiting ourselves to the degenerate subspace. Control Z. Sorry. P1 is some K not in the diagonal, not in the degenerate subspace. K. So you plug this in, so here, and want to reduce this to this particular equation. Okay. So again, there is no, earlier we mentioned that we had the lambda squared term, but because of the denominator is also involved the lambda, so the lambda at the denominator will cancel off with the lambda squared on top to give you a linear term in lambda. Okay. So this is all a bit confusing, but no, you see when the application comes, it's just quite simple actually. It's just like it's just like using the perturbation theory in a different setting where you have the degenerate subspace. Okay. So again, like before, for normalization, we set this to be equal to 1 rather than this. Okay. So this will not be equal to 1. So again, and then what we do is to use the power series again, okay, for this, and then the linear term for for this equation will produce back your the first order shift, and then your quadratic term in lambda squared there will give you this equation. Again, you need to check this. No. It's confusing in the beginning, but no, in the end, no, when you do the calculation, it should be sensible now. Okay. And from 5, what is 5? I can't remember now. Okay, from that equation, which is your Schrodinger equation, that sort of Schrodinger equation in the context of the degenerate subspace. What do I want to do with that? 5. Okay. Yeah. So that equation, if you remember, what was that equation 5? This is like your Schrodinger equation, right? So in other words, we have an operator here, but this part is your eigenvalues now, and this is like your Hamiltonian. Okay. So you can actually see that your P naught L naught is going to be eigenvectors of your V. Okay. And then because of equation 8, just let me scroll back. Equation 8 is that. Equation 3, let me see what that is. Oh, that one. Okay. No, you have to do the algebra. So I'm not going to do this over here, but you have to check for yourself. From 8 and 3, one can actually get your second order shift. Okay. Again, it looks a bit complicated, but no, in the end, you see we have an example after this. You see that this is quite normal thing that we do in the case of perturbation theory. So the idea is to identify the unperturbed eigenkets which are degenerate. So you have to check the level of degeneracy So in this case, if you have a G-fold degeneracy, then you should be sort of diagonalizing this G by G matrix, okay? Solve the circular equation to get the eigenvalues, which are now in terms of energy shift, okay? And then you diagonalize your V matrix so that you don't get off-diagonal terms, okay? So, and then you use again all the this is non-degenerate, so I have to correct that. Non-degenerate perturbation theory that you've seen before. You can use all the formulas apart from the case that your sum is now excluding contributions from the degenerate subspace. Okay, so these are things that no, the complications that comes from having the state space to be divided into two. One is from the degenerate subspace, and the other one which is not degenerate. Okay, right. Let's look at an example. Okay, remember we had before in the non-degenerate case, we considered a hydrogen atom without spin. Okay, being put into a potential which is involving a uniform electric field. Okay, and in the previous case where you have non-degenerate case, you are only limited to the case of the ground state. Okay, because the other states n and m for non-zero n, you have degeneracy coming from all the angular momentum states, angular momentum quantum numbers. Okay, so in other words, we have only considered the case of the ground state in the non-degenerate perturbation theory. Okay, because that case is the one where you have non-degeneracy. The rest of the terms are going to, the rest of the states are going to be degenerate. So in other words, what we had before in this particular case, you had the one we call as quadratic Stark effect. Okay, so now having done the formalism for the degenerate perturbation theory, one could actually try to do this again, and for that we need some simple example to start with. We start with the case of n equals to 2. This is actually wrong. Sorry, I should redo this again. Doing this is actually n equals to 1. Sorry about that. N equals to 1, then L equals 0, m equals 0. Okay, because your L is always less than n. Okay, so this is wrong. Right. So set the next case, which the simplest case for the degenerate case, which is n equals to 2. Okay, where the degeneracy comes from is from the 2s state or L equals 0 state, okay, and the 3 L equals to 1 state, which is what we call the p orbitals. Okay, so now we use the previous degenerate perturbation theory using this potential, okay, in such a way that this potential operator, the potential energy operator, will now have vanishing off-diagonal elements. So we need to find combination of your NLM states to make it into your matrix elements of V to be diagonal. So That's our main task over here. Okay. So if you look at the operator here, remember we have this z, and that z is actually coming from the called position operator. Sorry, position operator, which can be written as a spherical tensor. What is this? And I'm doing this in a rush. Spherical tensor of rank 1, which is a vector really. Okay, with z to be the q equals 0 component. Okay, q equals to 1 will plus or minus 1 will correspond to the combination of x plus or minus iy components. You recall back your spherical operators. Okay. So what happens in that particular case? Okay, you have some condition about for example, you have m dash equals to q plus m. Here q equals 0, so that means your m dash and m has to be the same. But we have another thing coming in from the fact that pi x pi inverse is equals to pi is your parity operator. And this is equals to minus x. Okay, so the only states that comes into play in the matrix elements will be the one sort of what you call sort of taking what should I say? If the states must be your state Lm, for example, has definite parity, which is minus 1. Let me write this properly. Has parity minus 1 to the L. Okay. You have to go back to the previous lectures to look at it. And then you want it in a way that under parity operation, it goes to the opposite parity. So in other words, those with let's say you have your parity minus 1 to the L, you will go to go to a parity state minus 1 to the L plus 1. Okay. So in this particular case, when n equals to 2, there are only two possibilities. It should connect the states L equals to 1 with L equals to 0. Okay. So let's write down the matrix element in this particular case. So this is L equals 0 state. This is L equals to 1, M equals to 1. And the other two is actually M equals 0. The other two is L equals to 1, M equals to plus 1, and this one, L equals to 1, M equals to minus 1. Now, why are we doing this? Usually when the normal convention, what we did was to write something like this: L equals to 1, M equals to 1, L equals to 1. This is normal case. Then you have M equals to 0 in the middle, then L equals to 1, M equals to minus 1. This is the normal way we arrange your matrix elements. But in this particular case, we want to use this instead, simply because we want to make the potential matrix element looks like something that we already know before. Okay, so then let me just explain this in a minute. So now what we only have over here, the rest are all going to be zeros. Okay, all this other matrix element is going to be 0, apart from the one that connects. So remember that this is also, maybe I should write here, n equals 0 here, n equals to 1, n equals to 0 here. Okay, and then the same thing repeats towards the row. Okay, this is the column, this is the row. Okay, so L equals to 1, m equals 0 will only make connections with the case of L equals 0, m equals 0. Okay? So that gives you the this particular non-zero element, and then this case will connect with L equals to 1, m equals to 0 case will only connect with L equals 0, m equals 0 case. So the only non-trivial case that we are looking is this top 2 by 2 matrix. Okay, because the rest are going to be 0. But if we look at this, okay, these are going to be equal. It's equal. You can calculate this explicitly to be equal to that. So this is the same value, and this is just like your 0, 1, 1, 0 matrix, which is your sigma x. So your sigma x is non-diagonal. Okay, you have off-diagonal elements here. So what do we do in this particular case? If we diagonalize that, then we change basis. Here we use the spin z basis, right, to get this form of sigma x. If you change basis, so you need the eigenbasis of Sx. Okay, so when you use the eigenbasis of Sx, then this will change to 1, 0, 0, minus 1. Okay, provided you use the eigenbasis of the x component to diagonalize this. Okay, so we do the same over here. So remember, in terms of your plus minus x thing is equals to this is from the spin lectures. It will be just plus minus. Okay, so this is your Sz basis. So this is your Sx eigenvectors. Okay, so in other words, it's a similar kind of problem. You focus on the top 2 by 2 non-diagonals. Okay, so that explains the reason why we are not using the normal convention over here. So we just want that part to be looking like that. Okay, this thing looks like this thing. Okay, so that's the only reason. And you use the result for the case of the spin x case to actually deduce the new basis for this part where you have the degenerate subspace is to use this states, this linear combination of states. Okay, so once you use this linear combination of states, then the first order shift will now be given by that, which is precisely that. So in other words, you get 1 minus 1 here, multiply 3e. Okay. So that's the no, and you can see that this is just all the complicated things that we have done for the degenerate case was just to make sure that our diagonal elements, your off diagonal elements of your potential will have zero matrix elements. Okay, and this corresponds to this kind of shift. This is the first order shift, so you get this state to be shifted upwards and this state to be shifted downwards. And the first order shift, you can see that it only depends on this electric field here linearly, so and that is called the linear Stark effect. Okay, and these states that we have just written over here is an energy eigenket with n equals to 2, but they are not parity eigenstates. So that's why we can now have a non-vanishing dipole moment. Okay? If it's a parity eigenstate, then you have this problem of pairing up the opposite parities. Okay? But this is not, so you can have that state. So, okay, I hope that sort of explains why the theory is a bit complicated due to the degenerate subspace that we're focusing in, but the idea is still the same. Okay, it's just diagonalizing your potential matrix elements in the degenerate subspace. Okay, there's one fine point at the end of this particular section is the fact that while we use the idea of your 2s and 2ps, 2s and 2p states to be degenerate in our what I call example above, okay, in reality they are not really degenerate. Okay, why? There is a spin orbit interaction. Remember that the thing that we considered earlier was a spinless hydrogen atom. Okay, spin will come in the context of relativistic ideas. Spin will come in, and there will be a spin orbit interactions inside the hydrogen atom. Okay. So when you have spin orbit interactions, then your p states will have will split up into two, p with 3/2 total angular momenta and p with 1/2 total angular momenta, and they are already separated due to these spin orbit interactions. Okay, but we still have coming from L equals 0, which is your s orbital. So this could still be degenerate in the context of a single particle theory. Single particle theory is essentially what we call quantum mechanics. But quantum mechanics is not the final theory, because when you consider a much more refined theory, which is quantum field theory, okay, where you have this idea of quantum electrodynamics, even in this particular case, where in a single particle theory, these two orbitals with the total angular momentum here, which is equals to half, okay, while it's degenerate in the single particle theory, it becomes non-degenerate again in the context of quantum field theory. And this removal of this degeneracy from these two states here is called the Lamb shift. Okay, one of the key things that when you learn the first time in quantum field theory is actually to calculate lamp shift. Okay, but I don't think we can do that in this context until we at least introduce the idea of relativistic quantum mechanics, and then after that we'll do quantum field, okay, but not in this course. Now then you might say, so why do we do all this degenerate perturbation theory? Well, the degenerate perturbation theory can still be useful if your perturbation matrix elements are much larger than your lamp shift. Okay, and if they are larger than the lamp shift, then your energy shift will be linear in E, which is the thing we discussed before, and hence, in other words, this degenerate perturbation theory is still valid. Okay, but if in the case where your perturbation matrix elements are smaller than the lamp shift splitting, then what we're going to get is your energy shift is going to be quadratic, okay, and that is actually coming from the case of the non-degenerate perturbation theory. So that more or less what I want to say today. There's few hiccups along the way, but essentially if you do the algebra of all the calculations, it should come out right. I will come back to that thing that sort of get confused a little, probably in the next lecture. Okay, so let me take so this is considered as the replacement lecture for the one we missed in Thursday. So let me see where do the interface is already changed for Google Meet. Okay, so I'll end this today. So sorry to disturb your holiday today. So if there are any other questions for today's lecture.
Yes, doctor.
Okay. Okay. You will have your test on Monday next week. Okay. So your assignment, I guess, should be handed in by at least Friday. Is that okay?
Could we let you know, doctor?
Pardon?
Could we let you know by Friday?
Okay.
Said already. Okay.
Because then I will be able to write out the solutions, and then okay, so you can prepare for your first test, second test. Sorry.
Doctor, what's the exact coverage again? Up to which lecture?
It will be the chapter on the discrete symmetries. That's all I'm going to going to examine you for test 2. Okay, I can't remember what lecture that is, but it's the one on parity, and then the lattice, and then the time reversal. Okay. Okay, that's all for today. Thank you, everyone.